Hey everyone, welcome to this video. I'm here with Greg Polson at Xometry. Xometry is a supplier that handles CNC, 3D printing, sheet metal, injection molding. Greg leads the application engineering team in on-demand manufacturing marketplace. He's your go-to guy for learning about design, manufacturing, different manufacturing processes, industrial additive manufacturing like 3D printing. Greg's background is in product development using rapid prototyping, focusing on the various applications of industrial 3D printing and advanced manufacturing. Greg, how are you?
Doing very well. By the way, I helped write that bio there, and now I feel like I made you out of breath, and I apologize for that. But yeah, we do a lot here at Xometry. We make a lot of parts, and simply put, and part of my job is I'm kind of that in between someone who's doing the design and they need something made. So a lot of times I help review files, look at drawings, even help customers figure out, what materials, what process to choose and why, so often answer that why for them.
Absolutely. Well, it's great to have you, and thank you so much for your time. I should probably explain what led up to this video. I got a random call from someone at Xometry, and somehow the topic of hobbying came up, and Xometry gets a lot of hobby people that request your services. And I immediately thought about the people who watch my channel. I get a lot of people in that demographic. So one thing led to another, and here we are. So the point of this video was to talk about, what level of hobby that Xometry can provide. And I'm not getting paid to make this video or anything. It was totally my idea. And, how just answering common questions that viewers and subscribers have about using a supplier, especially for hobby work.
Yeah, absolutely. And I think it's really important if you don't mind, actually, I can show you Xometry site really quick to
Mhm.
kind of give you a glimpse of why it's so accessible. And also, I think what you're doing is really cool because part of the freedom of manufacturing that has occurred in the last decade, really, like, in the last 5 or 6 years, it's been skyrocketing, has to do with 3D files.
Mhm.
What can I do with a 3D file now that I wasn't able to do before? So let me I'm going to steal that screen for just a second here. Uh, so Xometry, as you mentioned, we do manufacturing as a service. So this is the Xometry website here. And you can see we have a lot of different technologies that we offer. So we're not just a 3D printing house, we're not just a molding house. We offer a gamut of technologies. And I know it's not the topic of this, but even, on the material side, a lot of professional manufacturers and hobbies alike actually we have a supply side where we sell aluminum, acetal, end mills, cutting tools. So a lot of people who are running hobbyist CNC machines and milling platforms actually use us for that side of the business. But we offer access to all these technologies, really starting with a 3D file. And I just want to show how easy and straightforward it is that the site is completely free to use. And when you, I'm already logged into a quote here, but when you upload a file, you instantly get a price. So this is just logged in, get a quote. You can see that it accepts, steps, solid part, IPTs, PRTs, SAT files. Actually, I'm going to take something from my parts library just to make it a little bit more straightforward for me. All right, there we go. And actually, funny enough, this is a file that we were recently, I was on a webinar with folks doing Fusion 360, and we designed and prototyped this file. So I'll use this as a crossover. But the second that you upload a part, it's interpreting the 3D geometry of that part, and it prices out in the gamut of our processes. So within a few seconds there, you have a price. So this is a price, lead time, and if you're ready to go, you can check out right away. And this is actually, this material here is HP multi-jet fusion, so it's kind of a like a gray material here that prints in nylon. But that just happens to be the lowest cost material option that you have for this particular geometry at quantity one. But in seconds, again, you can continue to configure. So you have a little bit of 3D view, or you can see the part. This part's about 2.2 diameter here and 1.4 inches tall. And just as easily, I could switch between different 3D printing processes. So we have 7 3D printing processes available. So say I actually want to make a, SLA print in like a clear view, which is a translucent material, and I want to give it a kind of a clear gloss finish. I could update that, get a pricing right away, just as easy as if I want to actually just totally CNC machine this part and make it out 6061 and mill it out. And I could change finishes, I could change tolerances, I could even add stuff like CMM inspection right on the site, but they're all checkboxes away. So one of the superpowers that Xometry has is for people to be able to kind of spec out that work. Looping back to hobbyists, what that means though is you now have access to millions and millions of dollars of technology with only the need to buy like one part at a time. So, some of these sometimes our parts start at, like for SLS and some of our basic 3D printing, they're in the tens range, 10s to 20s range for smaller parts. You saw this one started out about $30 or so. So the barrier to entry is like much, much lower than it's ever been by price and just the access to CAD. But yeah, it's a really useful site for what you're, for kind of configuring, looking at your files and looking at different materials. So even if you are 3D printing, you can find a material that you may not have access to, like nylons or Ultem or metal, instantly on the site there.
Back at my university program, we said expense per minute to run a CNC machine was a pretty reasonable metric to use, and to get that kind of price out of a CNC machine is pretty impressive.
Yeah, and I was going to show I was showing the CNC there and showing quantities because a lot of what we do is we cut a lot of aluminum. Aluminum 6061 tends to be the most popular machining material out there. I actually got a bunch of CNC parts beside me. But we cut all shapes and sizes. We do finishing, tabs, inserts, you name it. We have the processes to do that. So it's very shiny back here. But this is actually a kind of a 3-axis surface part. But I have a very wonky part here, which would be completely 5th-axis machined and surfaced to get all the features on here. But again, for the customer, all they need to do is upload that file, and their price just pops up and they press buy. Like it's a much more streamlined approach to the typical RFQ, like, can you do it process. It's like, yeah, we can do it. Here's the price. And we can work the details out.
Wow. That's convenient. I know in my experience getting quotes, I've uploaded like 5 different versions of a part to try to game the price,
Yeah. Oh yeah. Before Xometry, I was a buyer. Like I worked in, you mentioned I worked in product development, and part of my job, so I ran additive manufacturing. So we had an SLS machine where I worked. So I was running that lab, and I was actually, work with clients on making parts. But internally for our product development team, I was usually the person to source the weird, like source stuff that was either like different additive technologies to try out or hard to source parts. So I did that shotgun approach. I would, go shoot out, 5, 6 different quotes to different people, wait, often days to get those responses, and then you get pricing all over the place, and you have to make a value call. Like, have you worked with them, and figure out if it's going to be quality, and if the price is really low, you're kind of like, do they understand what they're doing, and working through that. So that instant quoting that you saw on Xometry's site is all actually AI driven. Like it's learned through what's called machine learning, and we've been doing this for 6 years over tens of thousands of orders and beyond to actually train the pricing based off like what the marketplace actually charges for this type of work. So that's why you see that pricing show up so instantaneously, is because even though that geometry is brand new, never existed in the history of mankind, that's never been quoted before, the second it shows up, we know that parts like this in this geometry with this type of material, these type of features, this type of finish, this type of certification tend to cost this much money on a competitive marketplace.
That makes it pretty easy. What kind of hobby projects are you getting?
So yeah, on that note, I have a lot of times there's small brackets, custom, kind of customer sizes sub 10 requirements. I've actually been seeing a lot of work to uh, like trick out electric bikes. We actually have a customer who uses us for their kind of side hustle with a specific brand of electric bicycle that they're enthusiasts of. They create kits and things for different holders, different pieces, and they're getting one-off orders for these unique designs. And what's cool is they could just quote use the site and get that work on board. Um, I think this is a good alternative for if you can't afford a 3D printer, or like I said, if you don't want to deal with the time and investment it takes to kind of keep a 3D printer up and tuned. We have that instant access to just kind of like make parts. If you need a bracket, if you need a like we've done actually sometimes around like around holidays, if you need like something for like costume, or if you need something that helps just is a daily life helper, like a little tool or something to hold your specific set of tools together, tend to see those designs come around. That being said, when I go look at the mix, like especially in a process like selective laser sintering, it's all over the place. We have extremely robust, well thought out engineered mechanical designs, often built in semi-production, right next to like right next to that cup holder, or that one-off prototype. Like you have a high variety, and that's kind of like one of those magical powers of 3D printing you could do.
That's a good point, and I should, if any viewers have any questions, I should break down just simple 3D printing processes. You have
Yeah,
FDM, which is your basic desktop 3D printer like Robo R1 or Creality or what have you,
yeah,
where you have an extruder that moves over layer by layer. Yep, there's a
yeah.
good FDM example, and
So
then
yeah, you see that you love the layers on FDM for sure. Yeah,
yep, you have SLS, which is you have this pool of resin and a laser will cure it layer by layer, and that gives you more of a rough end surface, but one that is very strong. So if you need strong parts that aren't smooth, that's a
yeah.
good SLS example there.
I I'm an SLS fanboy, by the way, because I've been running SLS machines, or I've been at least I started my life in additive running SLS machines back in 2007. So uh, I ran an SLS lab. I learned about it when I was in grad school at JMU. And even when I joined Xometry, that was the very first thing. Is like I'm like, you got to get SLS on board, like because we were offering polyjet and metal sintering and some other work. So I was like, you need SLS, and so I call this like the 80-90% tool, because it tends to be one of the most cost effective ways of printing, and it's just mechanically really strong. But the beauty of it is you don't need support structures. So if I have like a little piece like this, or say I'm making like 10, 20 little pieces in my build, I can literally just kind of nest them right inside here up in Z, and just fill up my build that is about 13 by 13 by 23 inches with parts. So that's why like it could get so cheap. Is it's not necessarily that the material is cheap. In fact, it's like usually around like $88 a kilogram. It's actually because you're packing SLS with so many parts that it actually tends to get very cost effective. Uh, Anyways, I give it's a special place in my heart for SLS here.
Oh, that's awesome! Yeah, and then you have SLA, which
Mhm.
the print bed goes down into this puddle of resin. Laser cures it that way and up, and that's what I do the most of in my job. But
Yeah,
it tends to have a lot smoother surfaces, but the parts aren't quite as strong.
yeah. Strength is always a concern, and one of the things with SLA parts is they always cure. So, like, I'm not sure if you have an old SLA part at your work, but do they ever look like this?
They do.
Yeah. So they start. I have one like in the aging process by my window here. So sometimes the SLA starts clear, but if it gets exposed to UV light, it'll start to tint, because it is a UV cured substance. So it'll kind of start to brown. So you can see like the direction of the sunlight and how it hits this part here. That being said, like SLA is not meant to last, forever. It's meant to prove out a concept and a design, and it's one of the best in class technologies to do that because it's almost direct to CAD accurate.
Oh yeah,
Yeah.
we've had. I work in the medical industry, and I've seen surgeries done with SLA parts.
So like a surgical guides and things like that.
Yeah, it's pretty. It's a
Yeah.
pretty impressive process. So, I mean, on your end, how has CAD been influenced by some of these processes like CNC, 3D printing, sheet metal, and how do you interact with CAD as a supplier when a customer gives you things?
Yeah. Well, definitely. As I mentioned, we take most major forms of CAD.
Mhm.
And so like if you're a lot of times if you're in a professional engineering situation, maybe using SolidWorks or Inventor or Creo or something like that, and usually you're able to export your native, upload directly to our site, or if anything, you could convert to a step, which is kind of like the PDF of CAD. In fact, actually, because Xometry, we're connected with manufacturers all around the world, so a lot of our fulfillment is actually done with a manufacturing partner network. It's kind of like the Uber for manufacturing. Step file is usually what we're converting to because it could be read by everybody's CAM program.
Mhm.
You don't need specialized software. Like if you have your particular software, usually it could be interpreted that way. But I think for me, like CAD, like what I've seen in the last decade is uh, I started off with like SolidWorks because I had like a license or like as a student, but it's impossible for me to have SolidWorks as a personal use.
Mhm.
Like it's just financially doesn't make any sense. And that's a decade ago, and it still kind of is like that right now today. But meanwhile, like 3D printer came out, right around 2007, 2009, like the MakerBot cupcake, rep wraps were coming in, and people were like, look what I could do with 3D printing. And the very first thing that you get a 3D printer, you're like, oh great, I can make anything. It's like, and then the next question is, got a STL? Like, it's like, oh, I need this. So there's this huge demand for accessibility to CAD. Like I actually now want to create things, but most professional CAD programs weren't that accessible. So over this last decade, I've seen more and more accessible CAD, and I know like I'm looking at your hat right now, and you know that we have there are so many different CAD softwares right now that are actually free or low costs to get into a design, and it wouldn't have happened if it wasn't like for motivations like 3D printing, where it's like it's low cost to access manufacturing now, and you can throw the design rules out the window too because it's pretty forgiving. But now I just need a file, and I've seen this kind of ramp anti-ramp where it's like I have a printer that could do this much. Now I'm building CAD that could do this much, but my printer needs to be more capable, and now my CAD needs to be more capable. And what you could do at home is just pretty amazing.
It is. I have a 3D printer right behind me, although it looks like I have the world behind me. And if I have my 3D printer at home and I say, well, I can make my own stuff, what would some of the differences be between my desktop 3D printer that I bought for 1,000 or less and what
Mhm.
Xometry has?
Yeah, so everything we're running is industrial additive manufacturing. So these are usually machines that, on the low end are in the tens of thousands. Many machines are, in the hundreds of thousands of dollars. And uh, it's interesting because if you compare like layer line to layer line, so I have like an FDM part here. And by the way, I always have props. Like I'm surrounded by parts. My desk is just parts. So this is why I could just pick stuff out of the air here. But I have an FDM part here, and you could visibly see the layers. It's pretty good. It's a pretty good print. This is actually polycarbonate. This is a medical grade polycarbonate. But you can see the layers on there. And in a desktop 3D printer, a lot of times you can tune the layers and work and get a finer detail than what you could do in industrial. But um, what when someone's using industrial additive manufacturing, a lot of times what they're doing is they want to make sure the parts are consistent time to time and they're reliable on the lead time. So I can array 40 of these in a build, the bill could say, come back in 88 hours. And then I come back in 88 hours and I have my parts finished up. And so most of our industrial processes are built around reliability, consistency in product, and they are tuned in such a way that I could give to you, like, so if you're a hobbyist to, aerospace engineer,
Mhm.
you have a reliable sense of what you're going to receive. I could give you a data sheet and say, like, this is going to be the mechanical properties of the part that we produce. So the biggest difference that I see between industrial from a structure standpoint versus like a desktop is a lot of the expectations are managed on the industrial much more consistently for engineer work.
Mhm.
Um,
That's a good
eh,
FDM part, by the way. That
eh,
looks really good.
I think every time you have like a nice smooth contours, it's really nice. I actually did the test with this. I put these through an autoclave or type environment to test out different plastics. So I did this video called "Will It Beat the Heat?" So if you go on Xometry's YouTube page, you can find that. But this is polycarbonate, medical grade polycarbonate. This is what happens for ASA. Um, so so just kind of like you talk about, we always talk about in 3D printing, the pot handle test, which is the worry that we have with the accessibility to manufacturing items like 3D printers is the shape is not actually always the part. Just because you can make a shape doesn't actually mean you can make the part, because the part actually has to do with like the application behind it. And the pot handle analogy is always like, someone 3D prints their pot handle breaks on their boiling water pot, and they 3D print a PLA handle, and then they pick it up, and the boiling water spills all over them. It's a lot of the spheres have been curved, but that's like something you hear from time to time. I will say the accessibility that I have for materials and grades of materials in industrial is just so much higher because these machines there's like we offer 8 different manufacturing additive technologies. As 7 of them are auto quoting. Each one of them has their own niche, their own sweet spot, and some properties you just can't get with an open air system, especially like some metals is a really good example there. And some of these materials are very tough to handle and require very specific environments to run. So I have so carbon digital light synthesis is a higher end 3D printing platform that's really good for lattice structures, serialized components, but it actually has a kind of a secondary thermal cure to the materials that makes them cure into like urethanes. So instead of casting a urethane, you can actually print the urethanes, and you get like super good mechanical use. So I have like a little grid that's actually about a Shore 68 elastomer. And if you ever see like those Adidas 3D printed Adidas shoes, like this is the same material here. It's just a green material of this brand here. But there's some very specialized materials that are just would be very, very difficult to handle and maintain and probably cost prohibitive. Right now, right now today in 2020 in a desktop environment. Um, and there's safety factors there, right? Especially with like resins and photopolymers.
That's interesting. Yeah. And when you go to submit stuff, I know 3MF is the hot, new, cool kid format on the block versus STL. Um,
Yeah.
what do you see for the future of 3MF? And do you currently use it, or are there any plans?
So 3MF is it's definitely on the pipeline for us. We have 3MF conversations every day because color's coming.
Mhm.
Color 3D printing is like full spectrum 3D printing. It's accessible. In the desktop versions, it could be changing either the material feed itself. There's multi-feed extruders, and you can kind of do solid colors. But there's also kind of dot matrix style full spectrum printing, um, including ways to composite the matrix to change the properties of the material. So it's not just full color, but it's also like squishy to rigid to different properties in between that you could do with some technologies like polymer jetting and even HP multi-jet fusion, which is kind of an evolution of where SLS was. It's doing it. It actually has this detailing, excuse me, a detailing compound that you could actually tint and color. But STLs just don't carry enough information to be useful for anything. I don't know a single person in 3D printing who's like, you know what I love? STL files. I want 3MF because it provides me more information about what that part is, its size, its scale, and the details that may be necessary for it to actually be made right. And right now, it's really lacking there. Like obviously, I love step files. I love the file that I can manipulate in the CAD side. But 3MF is really bridging that gap as more complex requirements are coming out for 3D.
That's a pretty exciting development. I sat in on 3D Experience World 2020 where they went into detail about the 3MF file, and you can almost unpack it like a zip file, and it has things like color and texture and all sorts of things that you can't get with an STL. It's pretty exciting that that's in the pipeline.
I just have, hold on, let me see if I have this part here. So this is, do you remember ZCore Machines by any chance?
It doesn't ring a bell.
ZCore, they had to be fair, ZCore's been around for quite a while, 15, 20 years. They're acquired by 3D Systems, and they have it's actually one of the first 3D printers that I used as well, like when I was in grad school, but they have a full color 3D printing, but the material is kind of like almost like not really ceramic, but it almost had the consistency of like sheetrock when it was finished up. And but it did have inkjet cartridges on the outside, so it actually would color ink the outside and then make to make a color part. The problem was for an engineer, it wasn't mechanically very useful because you couldn't bend it, essentially, so it had no pliability. So when I was talking about color here, so this is actually a HP multijet fusion part that when I'm used to multijet, like, so what you buy on our website right now, which is still an amazing material, by the way, you could buy it and it comes out gray, or you could dye it black, but it's this is robust nylon material. But this is where that technology is going, where you could have actually a pliable, robust material that you can actually add spectrum color to. And what are the barriers to entry? First off, is the maturity of that machine. It getting more viable, having redundancy. Building on a network of reliability. That's what Xometry looks for, is having a reliable network of manufacturing partners. But I'm really excited about this because who has a black and white TV anymore? Like, so 3MF and printers, again, that ramp anti-ramp, like, they're working together to make some really cool capabilities that are getting closer and closer to like mainstream production.
That is cool. Can you do any colors as of right now, like 2 colors or?
So in PolyJet 3D printing, it does that dot matrix. A lot of times we're using it more for what feels like prototypes where you can do shades, but it's mostly grayscale. You can do full spectrum on higher end PolyJet machines. Is something that we source sometimes when it's required. But otherwise, like, when you talk about FDM and things, it's usually a single color. Like, we have 16 colors of ABS, but it's a single color. It's going to be yellow or green or blue.
Got it. Yeah, that's super exciting. Just when I thought 3D printing couldn't get any better, right?
Oh, I geek out about this stuff, as you could tell. And I'm always, one thing about me is like, for Xometry, we say we're leading edge, not bleeding edge, because we need to offer some reliability to our customers, because most of our customers are using these in some professional manner, like using machining services, et cetera. But I geek out when you have shows like you talked about 3D Experience World, or I go to trade shows for the industry, Rapid, other events. I'm always looking at like that next thing, the thing that's starting to show up on my radar 2 or 3 times, like a month, and then that there's adoption happening, because there's some really exciting stuff that's on the periphery. And I think for to this point, a lot of additive manufacturing, like, there's a lot of these technologies aren't new, they're just getting more stabilized for the printing aspect. So what's really enhancing them is that software, and like, going back to the 3MF and like what you could do. I'll even say this, the biggest barrier to entry right now for engineers into color 3D printing is how the hell do I actually color my file?
Yeah.
Like, what's a VMRL? Like, why, like right now, like a lot of our engineers, they're living in a black and white world too. Like when I talk about my CAD, I just have my SolidWorks gray part. I don't know what you're talking about.
Yeah.
But even that accessibility is a little limited. Like the best software for this oftentimes is a Photoshop, or it's someone who does more of a 3D animation or art 3D versus an engineered 3D. So even that stuff has a blend more together.
That's interesting. So for the part like what you're holding, just out of curiosity, would it be more effective to have a center of that part be a constant color and just kind of coat a skin of color around it so that you have more structural integrity? Or do you know how they are going to kind of approach that?
Well, what color is the inside of this? Take a guess.
It looks pretty rainbow to me.
Pretty rainbow. So, all right, off screen here. Let's go take a look here. Try to dig in a little bit. So, razor blade into my part. I'm gonna kind of fold it open here. All right, so if you don't see, I just basically just cut into this guy here. So you could barely see it on this one because it's so thin, but it's actually about a 1/4 millimeter of it is actually the color. The rest of it's jet black on the inside.
Oh, wow.
So multi-jet fusion, we're talking about SLS where that laser hits white powder, and that white powder will fuse by the energy of that laser and fuse its cross section as well as the layer underneath to give you that third dimension, that Z height. What multi-jet fusion does is instead of selectively fusing with a laser, it black inks the body of the part, that cross section, and it has this edging compound. So in this case, the edging compound has coloration to it. In this, in cases like this, it's just basically clear. And so when when a heat bar, just a single piece of heat goes across it, it only fuses where it's blacked. So where it absorbs the most heat there. And that's how you get multi-jet fusion parts. Is it actually is fusing by consistent heat, but only where it's dark is where it's absorbing enough heat to create that fusion effect. So the inside of these parts is actually jet black, which is kind of interesting.
Wow, that is pretty phenomenal.
Yeah.
I had
by
some.
The way,
oh, go ahead.
By the way, yeah, I had a guess, pretty educated guess on this, but actually I hadn't tried this before, so I'm glad I was right. But
that's
yeah,
right. Well, a part has been sacrificed for this video, so I hope all the viewers are grateful
for our education.
Yeah. I had some questions from some viewers, if you're interested in jumping into that.
Yeah.
Let's see, I have one from Kyle. He says, at what point does going through a supplier for injection molding become more cost effective than self-molding, like using urethane resins and such? And what quantity of parts would need to be considered to justify the cost of machining a metal mold for injection molding? And then, oh yeah, go ahead.
Oh no, I think what was the follow-on to that question?
Oh yeah, and then there was an update that he's looking for an end product that would be a sport stick like underwater hockey, which sounds awesome. Which is it's a fairly small sport, so we'd be expecting a massive quantity of sales. But he's trying to find that sweet spot of injection molding versus other processes.
Yeah, so injection molding definitely has a higher upfront cost because you are machining out a mold tool, and it's being run on professional equipment to hold them at high clamping forces as it ejects molten plastic in. The pro of injection molding is in quantities. There's a reason why from your keyboard to your dashboard everything is molded plastic. Is once that tool is created, it is super repeatable to make these parts, and it's cheap on a per part basis. When I do urethane casting, so I'm usually, in my mind, urethane casting is usually like a 5 to 50 job. Now I'm also talking about like professional urethane casting, like so services we're usually like measuring, inspecting parts and doing it's so it's not just like a resin cast. We have some specialized equipment for that. But when I'm urethane casting, what I'm usually doing is my very first thing I do is actually I do a SLA run. I'm actually 3D printing. I make my part. So I'll call that a master pattern. And let's take this up. So like, say I'm making this part right here. I make my master pattern, and then I will essentially create a little custom box, fill it up with a rigid silicone, and then fill it up on the other side so the part is just basically suspended in the silicone here until it cures. And then I cut it out, and now I have two halves of the silicone piece with a void in the shape of my part. And I inject in this two-part compound, these urethanes, similar to like if you have an epoxy stick where it like has those two parts, it cures together once they're blended. Urethanes work the same way, and I get that curing. So urethane casting is quicker because you don't need the technical tooling aspect. You need a 3D printer. You need to be able to have the special, like the equipment to make those tools, but you're not like machining them or anything. So it tends to be quicker and lower cost on that upfront side. But you could quickly see that a lot of the costs of urethane come in time and labor, because now per tool that I have to wait for my cure time per part. And I have to release a part, demold the part, reset. So my output per day, really, like in a good day, a lot of times in urethanes is like 8 to 12 parts. So when I'm doing that balance of like when does it make sense, and that's why I always say urethane's more of like a 5 to 50 rule. It's about like it's great for end use product validation, but if I'm even working in the hundreds, I may be looking at an alternative process just because the output that I require there. There are actually low-cost molding options. Aluminum tooling's available. Sometimes if you have smaller parts, molds they're still going to be in the thousands or like between 1,000 2,000. But in the more complex, molds could be $100,000 if you have high complexity and multi-cavity molds there. But like a lot of these things, like CNC machining and everything else, that price point is getting more and more competitive as time's going on. So sometimes a lot of projects we see 3D printing actually sometimes work for that low volume initiation versus what urethane casting used to do, because we have so many materials available. And then once that market's validated, they move to mold, and even at low volume production, it may still have actually a really good break even there.
Got it. That's pretty cool. And this is my own
Mhm.
curiosity. Would you ever see mold making be more economical with DMLS, direct metal laser sintering processes, rather than something like machining?
Yeah, so I'm very interested in this. So we work on a lot of molded projects. I get questions a lot about 3D printing of a mold tool.
Mhm.
Now, this is where that can work. And by the way, you can also do this. You don't need to do metal directly. You can also do this with SLA and some other materials that have a decent temperature resistance. But you can substitute in your tool certain features, like curvature features, and actually print those and add them to the tool, kind of assembly between like a CNC machine tool with like a 3D printed insert. And you can make a hybrid tool using some of the value adds that 3D printing has, like the ability to do custom contours and sharp internal corners and stuff, like without having to run EDM. But 3D printing of metals is not as smooth a surface from the natural print. So if I'm doing 3D printed metals, externally, if this is part of my mold core or cavity, I'm very likely post-machining it anyway. So the value add may not actually be on the external side. It may actually be internally. So a lot of times when you see like the best applications of 3D printed mold inserts, it's because they have like this swooping coiled cooling channel where they're flowing water through to actually keep that core cool as it's producing parts, because you're flowing in molten plastic. Obviously, that plastic's conducting into the heat, and the hotter and hotter those cores get, the more inconsistent your part can get, or your part won't release right, or it'll stay loose and kind of have some deformation when it's being released. So you have to keep your cavities cooled And usually it's just very rudimentary cooling channels where it's kind of like straight drill to straight drill and cap it in. And so it's kind of like, think of everything in that L-shaped pattern. But with 3D printing, I could get right up to the edge internally on that. And that's where a lot of that metal 3D printing value add comes in. But surface finish is definitely always a concern. I have a DMLS part somewhere around here. Here's a really good example. Now this part, by the way, it looks a little rough because it required so many support structures to make, but this is a metal 3D printed aluminum part. And if you look at that surface finish, it has a kind of a grainy matte finish to it. And that grainy matte finish, when you think about how injection molds work, would transfer directly to that part. So that's what your part's going to look like too. A lot of times we want parts to, look like that. And so that requires, a CNC milling option. And then usually like for that part there, it's probably going to be a bead blast or something to get back to that kind of glistening matte finish to it.
Wow, that's pretty fascinating. And I've got a question from Vorpal Gun. He says, I'm a hobbyist who's recently gotten into FDM 3D printing using a Prusa MK3 and who found this channel due to being fed up with the business model around Fusion 360. Oh, thanks for all the free CAD videos. Any plans on videos around OpenSCAD, CAD Query, or other code-based CAD? I'll answer that one right now. I can do VBS, VBA, Batch, a few programming languages, but I probably need to brush up on my scripting before I can present anything that is really of value. So maybe in the future, but not in the immediate future. So his question is what the view on the CAD software business model is with those who use the software professionally. As a hobbyist, I don't have the option to spend that amount of money, but I imagine a business has. But won't the ever increasing per seat prices still annoy small businesses? Is it just a case of the usability of the free and cheap alternatives being poor and thus there not being any realistic choice? Or does the option of getting support, etc., matter so much that something like FreeCAD won't be an option either way? Interesting question. Do you get very much FreeCAD or other CAD, or is it mostly you're just getting steps and STLs and don't even know what the platform is?
It's honestly really hard for me to tell what is coming in, but I definitely do empathize with that cost of ownership because I like CAD. I will 100% say I've been spoiled. Like I have SolidWorks actually open right now on my computer just because I've been able to use that in a professional setting. Use some very professional CAD software. So usually when I'm doing like a lot of my job is not making the files. It's more reviewing the files. So I need something I can open up a lot of different file types for. Kind of drive around, spin the CAD, so I can provide feedback to customers. And even on the 3D printing side, we have some specialized software like something called Magic, which is for industrial additive manufacturing. That's a super capable STL powerhouse essentially for that. But I'll say, like from an ownership side of things, you do have platforms that are bridging the gap where you can have access to make a pretty powerful file. And I think actually I was just looking at some of your videos and it's kind of amazing what you can actually do now with what quote unquote free CAD. Like it doesn't mean bad CAD. It's just it's open source, and the adoption. I don't know what the adoption looks like on an engineering side, but I think those capabilities are really meeting there right now.
Yeah, I personally believe that free CAD can be used commercially because I've done it so much in freelance and of course, certain aspects may not run as smooth as SolidWorks, but it's a really amazing program, especially for how powerful you can model stuff. And I think its influence can be felt even if it's not used commercially. You think, well, Fusion 360, Onshape, now you have Solid Edge that are all platforms that you can have a free version of. And would that be if people didn't have FreeCAD or they didn't have FreeCAD for a hobbyist to compete with? And I don't know, but I think it's kind of worth considering that maybe FreeCAD is still influencing these big platforms in a way.
I think it's true. I mean, it's just like on the desktop 3D printing market versus industrial. I think sometimes, sometimes my frustration is industrial doesn't keep up with the speed that's coming out with like desktop slicing and even things like when you're doing FDM infill patterns. Stuff that I would love to have access to on the more professional side, but a lot of times there's a lot of reasons why those products are not always quickly updated, but I think these accessible platforms help keep everybody on their toes.
Absolutely.
I will say there's some cool stuff that you can do with more professional programs. So I have like this topology optimized part here, and things that where I want to see CAD evolve to will be not just these feature additions. So it's not just like extrude, create holes or things like that, but being able to intuitively make lattice structures, intuitively make some sort of topology decisions, even surface textures, like the ability to actually add a surface texture to your part. So when you 3D print it, that texture is applied already. With 3D printing, like with molding stuff, you don't think about that. You're just like, oh, we'll do that in the tool. But in 3D printing, it actually is amazing what a surface texture can do to help mitigate some of that layer looks that you'll get when you print. Like just adding a simple texture to it actually can make a part look amazing directly off the print and make it more viable for end use. But I hope CAD evolves to the way that, like, I almost think about this from a design for manufacturability standpoint. Like when you make a typo and you get a red underline, or if you're texting and you don't even get the underline, it just corrects it for you. Like, I think the future of CAD is going to be with practical manufacturing in mind. So like as you're designing for a product, it's already shifting and editing in real time to compensate for any manufacturability issues that may be coming up as you're designing. Like just like a word processor does. And right now CAD it's not quite there, but even on the professional side, but I think that's where we're going. And I hope that trickles, I hope there's competition on both sides of that.
Oh yeah, that's a great point. And topology is supposed to be on the edge of topographical optimization. And if there's any developers for FreeCAD watching this right now, I want to put a little bug in your ear, because topographic optimization isn't as bad as it sounds, right? If I just take a random part and put a force on each face, topographic optimization just meshes all this stuff up, and then it either rounds every section of the mesh up to 1 or down to 0, and zeros get removed, the ones stay. So it finds the least amount of material that you need to satisfy those forces. So if you're a developer for FreeCAD, you could probably use the Calculix solver to get that done. Be a cool feature to add in.
Hint. Yeah.
Yeah.
That's, like this part here, you see like weird little, free branches on the side. And that's exactly how this part was generated, was all the bosses were essentially fixed features. And then it gave some physical forces saying, this is what I'm going to be exposed to. And then it digitally connected the dots. Now, I will say this part is fantastic for 3D printing. Terrible for CNC machining. So sometimes topology optimization also has to do with what process are you ultimately doing, because this may look similar but may have more accessible like 3-axis approaches to the design. So if you're looking at different processes.
I've got 5 more questions here.
Yeah.
From TAH1712. A hobbyist isn't going to have all the ancillary equipment that a small business has or should have. A hobbyist at the early stages won't know many things initially, nor how to solve issues. So with an open question like that, do you get hobbyists that may not know how to solve some issues?
Yeah. So actually, I'm gonna run back to our website really quick here, if you don't mind, because I actually want to show some really cool stuff that we have.
Absolutely.
So let me grab the screen here. So again, this is just on Xometry site. Nobody knows a dozen manufacturing processes. Not even the best of us do. I try, but it's we all have our strengths and where we need to learn. One of the things that we've offer for free is free resources like design guides and a blog and other information. But if you're interested in learning about a particular process, I really want to encourage you to go to the resources on our page, click on design guides, and check some of these out, because every single process has its own little nuances and tricks to it, and this will help you kind of help manage your expectations. Because say you're going from SLA and say you're going from SLA and then you want to move to direct metal laser sintering, like your expectations are different, from price to build size to that surface finish we were just pointing out there. So having some information around that is really, really useful. But I do want to point those out. We also have a fantastic FAQ, so our little help center at the bottom here. So if you have random a random question like what's the build size for these, what parts can be sterilized, just search in the search bar there. It's very useful. I also, again, this is something I do for fun. I make engineering videos. So they're usually about, I call it edutainment. But we have a series called Will It, where I actually take different 3D printed parts and I kind of put them up to bat against each other in different tests and challenges. And that's also a good way to learn, because you can look at that data sheet all you want, but sometimes you're just like, but what if I do hit it with a baseball bat? Like, what really would happen? And that's kind of what these tests are about. Is just impact, flexibility, high heat resistance, and I do a lot of practical tests around that.
Fantastic. I have one from Daniel. How can we design parts for 3D printing that are easily transferable to injection molding in the future? And how much help should be expected when designing injection molds?
That's great. So first off, on the designing injection mold side, you need to work on part design. We'll figure out how to make the tool, and we'll tell you how, like, the drivers of that tool. Those design guides I pointed out are probably one of the first places to start with injection molding. But we always say like the holy trinity of mold design, or like part design for molding, is uniformity, undercuts, and draft. So if you are designing with that in mind, honestly, you're already designing pretty great for 3D printing. So uniformity is that uniform wall thickness. So creating an even wall thickness across your part. If you're doing like internal ribs, so like instead of adding, if you want to add something, a strake to your part, don't add just a bulk there, add ribs instead. So you keep a uniform wall, and those ribs could be like usually around like 40 to 60% the outer wall thickness. But there's a reason why you could cut a steak with a plastic knife. It's not because the plastic is strong, it's because the knife is designed for that type of motion, right? There's a backbone to it, there's supporting features. And the same thing goes when you think about mold design, is you could add strength and add mechanical properties. You just need to think in uniformity. When I talk undercuts, I'm talking about features where if I look at my part, and let me find a part in front of me here. I'm going to grab the CNC part, even though it's like, because it's probably one of the best examples for undercuts in front of me. But if I look at a part straight on with a mold tool, I could create all the features for this internal, and maybe grab some of the external there, and that's one side of my tool. When I look at the other way, I could create these whole features, create this feature right here. So I create it this way. Now, what is an undercut? If I shine a flashlight on both sides, it'll be lit, but the stuff that's casting a shadow, like these side holes here, is what I consider an undercut. Undercuts mean that within my mold tool, I now have to create a separate mechanism to go in and essentially plug that hole while the injected plastic fills around it, and then it needs to unplug itself before the part is released. So in a part like this, because this is kind of a terrible part to mold, because I have these weird off-axis features here, so I have to have 3 different mechanisms making this. A lot of times that's $1,500, $1,500, $1,500. Like you just added 3 to 4 grand by having those holes there. So a lot of times when you look at mold design, you're trying to think about how can I get my function, the cosmetics, what I need, while simplifying the complexity that the tool is gonna be. So that's why I think about undercuts next. Once you have that all in mind, draft. So that's the last part of that is draft is just, instead of having a complete parallel edge. When I'm looking on that from that mold cavity view of my part, like so if I'm looking like this, I have a little bit of an angle. And the best way I explain draft is, imagine if you had two paper towel rolls, like one shoved in the other, and then you try to pull them apart. It's just friction the whole time. Now take solo cups that are stacked in each other. The second that I move one away from each other, there's a complete air gap around that part. And when I'm injection molding parts, I am flowing plastic around that cavity. It's cooling to a hardened state. And now I have to move that cavity away without distorting that plastic part because I want to keep it in the shape that, the intended shape of the part. So by adding draft, I'm able to release that part the second that my tool moves away. So I don't have any deformities or any scratching or anything that could happen that will cause a cosmetic or a dimensional error on my part. But yeah.
And when you say that, it makes me think about, those Venn diagrams that you have some in common and some different. But I think that the Venn diagram for injection molding and 3D printing is injection molding is completely inside of 3D printing with some of the design freedom that you get.
100%. And like I said, I think you can always tell you can always tell when someone has that intention for injection molding in mind when in their design phase, or you often see parts in iterations, like where it's first just will the concept work? So it's just kind of throwing designs together to making a part, to where you start seeing it cored out, so it's looking more uniform, and you start seeing different features that would be injection moldable. And the better design parts are for molding. Typically, they work really well for SLA. They work really well for SLS. They work really well for these 3D printing processes. Where if you get over thick, it actually can cause like warping or deviations or misprints. So yeah, they really do go hand in hand. Now I can't do lattices and cool stuff like this with injection molding, but as you said, it's a circle inside that 3D printing Venn diagram for sure.
Right. You get kind of spoiled with the design freedom that 3D printing can give you for sure. One from TV Athome. One service nice to have would be cheap, detailed 3D scanning without the artifacts and thousands of digital bumps on large, smooth surfaces, and down to miniature scans with tiny resolutions. So I think perfect 3D scanning. Is that in the stars for Xometry?
So I've done several projects where I reverse engineered parts. I will say 3D scanning technology is getting better and better. However, if you give me this part, I will definitely just pull out my calipers and create it from scratch. If you give me a part like this, where it has all these contours, it's not something that I could easily caliper, and that's where I start thinking, okay, 3D scanning has got to be the way to go. The technology to get from there's even free 3D scanning stitchers and things like that, but to that point, you are lucky if you can close that mesh.
Mm-hmm.
Usually you're not able to close that mesh, and when we talk about mesh files, like that's just that triangular pattern of triangles and surfaces that you get from that initial scan. And to 3D print, you need to have a closed mesh file so it knows what's inside the part. So that is my part, and what's not the part. That's kind of how STLs in a nutshell. They're like balloons. Like it's either popped or it's a balloon. And that's step one. There's like 9 phases of fidelity when it comes to 3D printing, or 3D scanning, because I can't do too much with the STL file. So that initial mesh file, I can probably replicate it with the 3D printer, but I have those bumps. I have those, I may have some artifacts from the scan, and I can't really do anything about those. So there's software that can help you smooth out those features. But now, cool, I got a smoother part, but it's not parametric. Like I can't go and say, let's drill a hole, halfway through, or I can't even say what's halfway through it. There's certain things that you can't do. So a lot of times, if you see a professional reverse engineered item, it's almost like I think I saw your Corsair project where you had your 3 views,
mm-hmm.
and you were. By the way, F4U Corsair is one of my favorite World War II planes, so we have that in common.
Oh yeah.
But we had you have those 3 views, and you're drawing around that, it's kind of the same thing when I've friends who do this professionally 3D scanning. It's kind of the same thing they do, is they actually have really good software that gets it pretty close, but then ultimately they're using surfaces, they're using extrudes, they're using parametric features, and they're essentially drawing over that in order to get a full reverse engineered file that they could actually manipulate later.
Mm-hmm.
So there's a lot of stages in between. I wish it was more accessible, but it's not as accessible as a lot of people think. Because like even when you get that initial scan, there's so much work if you don't have the software to really manipulate it even further.
I've had the honor of doing 3D scan cleaning in SolidWorks a few times, and they come in rough. So
Yeah.
I totally agree.
By the way,
Mhm.
that same principle comes. Like I said, we can only 3D print STL files or with a mesh file, but we can't CNC with a mesh file. So sometimes you can see someone take a mesh file, drag it in SolidWorks, and then export it as a step. But unfortunately, it is not something that I could actually really manufacture against. Because say I have this and it's a STL file, and I import it into SolidWorks and then export it, what's really be is a series of lines and triangles and planes. And now I'm trying to import this into my CAM software, so my computer aided manufacturing software, and it's trying to look for a circle. All it wants to do is surface circle, but it says like plane, 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 and it can't actually identify the features of the part. So unfortunately, when that happens, we have to go back to our customer and say, you really need to, either redraw this or find the original native CAD format to export it to the right file format. If not, we're stuck with 3D printing or urethane casting.
You're totally right. SolidWorks and FreeCAD have the
And
functionality of
FreeCAD.
being able to smooth out those mesh files. So I better make a video about that pretty soon. It's a pretty interesting process too. But you're totally right. You can't your tool paths would be crazy if you try to do that with an STL.
Yeah.
I have one from RazTaz. When I print two parts that fit together on my own printer, it takes a few tries to get them to actually fit. So I'm curious as to how you would deal with problems like that when it's somebody else's printer that you don't know using a different material and it costs a week in shipping and $50 every try.
Yeah, I think that's a good question, and it really depends on the application. Keeping within the same family of processes is a good start there. Also understanding the nuances of that process and looking at design guides. SLS is a really good example where SLS has a pretty decent detail to it. And if you imagine, like I have, these mating features here, if I built a mating lid in SLS, very likely these would be aligned up just because the same materials, same properties, and generally it'd be like within that kind of plus or minus 5 or 6 thousandths tolerance, so 5 or 6 thousandths of an inch tolerance. Um, but I could also help myself. So I also know this: SLS 3D printing tends to have shrinkage in the holes because essentially the heat when it's fusing around those holes is radiating so close to the other edge that it's actually causing a little bit of over thickening as it's fusing together. So that laser hits and there's enough radiation to cause that thickness. So if I have a critical mate, so say I have imagine a kind of a tongue and groove. So my tongue feature and my groove feature, if I didn't provide any clearance, first off, plus or minus zero tolerances in reality don't exist. Like they just don't exist. So if you have a flush to flush clearance, you're in for a bad day in the first place. But say you want to assure that you're going to get a mate, even if you have like maybe a 3 or 4 thousandths clearance, you actually may want to take the groove portion of that and use a move face command or offset surface, whatever, depending on like what type of platform you're using, and push it out 6 thousandths. So that groove will actually be 12 thousandths wider in your CAD. But the hypothesis is this: that very likely that wall's gonna, if it's a thin gap, that wall's gonna offset on each side by about 4 or 5 thousandths. So by adding that 6 thousandths extra width, it's actually going to print closer to your nominal on that first go. So there's a lot of tips like that you'll find that are dependent process to process. But usually for me, one of my initial go-tos, if I'm ever designing for mating parts in 3D, is that I may offset at least one side of those mating surfaces by 4 to 6 thousandths, depending on the process, to help compensate for any overgrowth that happens in those mating features. Same thing, by the way, if I have panels, I may change some of those holes to slots, or just make the one side of the holes a little bit wider, give myself a little bit more wiggle room in there, and use other features of index.
That's a great answer. Yeah, and of course, if you're doing metal, you could probably just go to your LN1, LN2 fits or whatever. And then, from my
Yeah.
experience, when it comes to 3D printing plastic, uh, especially when it is, a bunch of money every shot, I usually just make sure that they're not going to be too loose, and then get out the sandpaper.
Yeah. So I mean, you just saw here, like, what do I have by me all the time? Like, if you look at someone who works in additive manufacturing a lot, they're they usually have like their bag of tricks, which is usually a bunch of files. I love dental tools,
Mhm.
file scrapers, razor blades, grabbers, cutters. Um, yeah, this is usually what you'll see by someone's desk who works very much in additive. And usually, like, if it was another day, I'd probably have a Dremel right if I had me too. If you are working on the prototypes phase, it is completely okay to cut into your part and get dirty. Like, these are not Fabergé eggs. I mean, you're trying, we're working together on purpose, and industrial additive manufacturing will bring you a very consistent result. So if that peg is not fitting, if you order it 300 more times, it'll probably still not be fitting 300 more times. But if you like figure that out and you're able to compensate in CAD, so say you do have to shave off, a little bit of this or sand it down 5 thousandths, if you compensate in your CAD, that print's going to be consistent too. So you're gonna end up being able to kind of tune your parts. And like I said, design guides really help there, where so you don't like lose $50, but prototyping is a process. Your prototypes are not your end product.
Right. And in my personal experience, like on Form 3 printers and stuff, I've usually had good luck with, like, kind of like what you said. I went with 20 thou, and I had a pretty good slip fit that way.
Mhm.
I got another one from Andrei Gabriel. What tolerances can be achieved by an industrial supplier? I think you kind of talked about that a little bit in your last answer. But
Yeah, so we have general manufacturing standards. I could actually, let me open this up really quick and I'll drive to our site in a second here. All right. So under resources, you'll have our manufacturing standards. And this goes through all our different processes and what are general tolerances per process. So these are industry accepted general tolerances. This is not like Xometry's made up tolerances. These are, what most shops consider, hey, from a standard manufacturing, this is what my expectations are. So some will be tighter, some will be looser. So like DMLS ±5 for the first inch is typical, plus or minus 2 thousandths for every inch thereafter. Now, with 3D printing, we always have a caveat, which is this. Designs that we get can be 3D printed because of the free form nature of 3D printing, and it's more forgiving about design features. But it doesn't mean that design is best suited for 3D printing. So if you have a part that is, has thick and thin features, or is designed like a dumbbell where it has like a thin feature in the middle and then two, like, barbells on each side, you could expect deviation of those parts that is, somewhat unpredictable, just because of the nature of the print. So yes, the printer can make that shape, but designing with manufacturability in mind, using DFM best practices will hold you closer to those guarantees of tolerances.
awesome. That's a really good resource. That's all the questions I have,
Mm-hmm.
Greg. I know you took a lot of time out of your schedule to do this, and on behalf of myself and everyone watching, thank you so much for doing this with me.
Yeah, I hope everybody stuck around. But I love talking shop. This is something that we live and breathe every day. We make a lot of parts for all different types of clientele and for all different types of applications. And I think the coolest thing Xometry has is that accessibility. So you provide the design, you can instantly quote, get that pricing, lead times, make some decisions. You can use it for budgetary. There's no commitments or anything, and you can compare. I lead the application engineering team. We have teams of experts on hand for every process that we have to help answer some of these questions as well. And of course, we have those guides. So I hope this was helpful. It's awesome talking to you. And like I said, I've been geeking out with your channel, and I kind of want to try some of the software that you're using now. But yeah, that's all I gotta say. So thank you so much.
Thank you so much. It's been a pleasure, and I hope to talk to you again soon.
All right, thanks, Justin.
Thanks.